Okay, so I'm going to try to go through this as quickly as I can. Well, not as quickly as I can, but at a relatively decent clip. So the first three, it looks like, through first four. So first three are pretty much the same, balance the equations, and then figure out which coefficient is in front. So we're just simply balancing all of these equations. 1, 2, 1, 1, 1. If you need me to walk through these, I certainly can, but I feel like you should know how to balance equations at this point. So simply there's a 2 in front of HCl, so D. Balance the following reactions to determine the coefficient in front of water. Again, we're just going to end up going back and forth. There's one carbon, one carbon, one oxygen, one oxygen. There are a total of 6 hydrogens, and there's just 2 hydrogens there. So 3 in front of that one, and everything should be balanced. So what's the coefficient in front of water? Should be C. Next one, balance following reaction, same kind of setup. If we look at nitrogens, I've got 2 nitrogens there and just 1 there. So we'll put a 2 in front. And now nitrogens are balanced. Now if we look through the next, nitrogen is balanced with 2. I've got 5. We'll do oxygens last, it looks like. Actually, we don't need to. 6 oxygens, 3 times 2 would be 6 oxygens on both sides. 2 hydrogens, 2 hydrogens. It squares away. 1, 1, 2 is the coefficients in front. So what's in front of nitric acid? Nitric acid has a 2 in front of it. So B is the proper answer for that. Okay. So this next one is a little bit trickier, but not really. We did it in class. This is, and you notice it's combining with oxygen. This is a combustion reaction. And we know the products of a combustion reaction are always CO2 and water when we're burning a hydrocarbon, hence CO2 being a problem in the atmosphere because we always produce it when we burn something. And so now it's a matter of balancing this out. So 4 in front to match the 4 carbons. I've got 8 hydrogens, and so I'm going to put a 4 in front of the water. So I've got 4 carbons on both sides. I've got 8 hydrogens on both sides. And now I'm going to add up the total number of oxygens. I have 8 oxygens over here, and I have 4 oxygens here for a total of 12 oxygen. And now I have to put a 5 in front here. So it's going to be 1, 5, 4, 4 to give me my total number of, yeah, so oxygen should have a 5 in front of it. And I think my dog is eating my lacrosse stick, so I'm going to pause this for a little bit. Crisis averted. Okay, so just balancing chemical equations. So let's take a look at this next one. Sodium azide, we recognize that sodium azide, we don't even have to actually look at the answers until we actually balance it. We figure out sodium azide because they're all the same. Na, N3, you don't need to know what it is because every single reactant is the same. So Na, N3. So if we're going to balance this out, we're going to end up with sodium solid plus N2 gas. If it's breaking down into its elements, and that seems to be what it's doing in all of the answers, that's what we should end up with. Now it's not balanced yet, but we can take care of that. I'm going to put a 3 in front of here, 2 in front of there, and we need there 2, 2, 6, or 2, 2, 3, but 2 sodiums, 6 nitrogens on both sides by doing that. So if we look through our answers, we're going to notice that a few of these get eliminated right away. We're going to eliminate A right away because this is not a thing that doesn't exist in nature. This also can be eliminated because this doesn't exist in nature. So we can just scribble those out. The next two, so C, this right here is the same thing as just a 1 in front of everything. So that goes away. And this one, C, is just not balanced at all. So it comes down to D ultimately as the correct answer. Yep. Okay. What is the empirical formula for the compound that contains? Okay, so anytime we do an empirical formula, we always have to figure out how many moles we have, right? Because we know that this is going to be Kx Sy OZ. So we need to solve for X, Y, and Z. We know they're molar quantities. we could go through, we could calculate all of those, or we could just do it properly. Here's my potassium. And I know that I have 49.5%. But if we assume we have 100 grams, we can just assume that we have 49.4 grams of potassium. 49.4 grams of potassium, convert it 1 mole over 39.098 grams. That's the molar mass of potassium. You end up with 1.26 moles of potassium. And you do the same thing for the rest of them. Sulfur has 20.3 grams. Again, molar mass of sulfur is 32.066 grams over 1 mole. We end up with, oh, these are both sulfur, potassium. We end up with 0.633 moles of sulfur. And then finally, my oxygen, which I have 30.3 grams of oxygen, sulfur, 16 grams of oxygen over 1 mole of oxygen equals 1.89 moles of oxygen. And so now we plug those values in. So potassium is 1.26 moles, sulfur is 0.633 moles, and oxygen is 1.89 moles. And we just divide by the smallest number. So each of them gets divided by 0.633, and you end up with K2S1O3 or K2SO3. K2SO3, which is C. So that's it. That's how we do those all the time. And so the only difference between those and a combustion reaction one is instead of the carbon being alone and isolated, we have to pull it out of the carbon dioxide. So in order to solve for the amount of carbon present, I have, oh, actually, sorry, this is just a simple one, same thing, 70.6 grams of carbon. And again, 12.01 grams over 1 mole, that's carbon. We end up with 5.88 moles of carbon. The hydrogen, we have 5.9 grams of hydrogen. Hydrogen's kind of an easy one because it's 1.001 grams over 1 mole. And you essentially end up with the same exact thing. And then oxygen, 23.9 grams of oxygen, 1 mole oxygen over 16 grams of oxygen, you end up with 1.47 moles of oxygen. And again, we plug those numbers in, 5.88. Hydrogen's 5.89. Those are pretty much the same. Oxygen 1.47. We're going to divide all of them by 1.47. And you end up with C4H4O. Again, this is the empirical. That's the empirical formula. So the empirical formula is not what we're looking for. So the molar mass of the empirical happens to be 68 grams per mole, but we know that the molar mass of the compound is 136. So the multiple that I need to multiply that by is going to be a 136, which is the molar mass of the molecular, divided by 68, which gives me an N equal to 2. So that just simply means I need to multiply this whole thing by 2 to get me my molecular. So C4H4O times 2 equals my molecular, which is C8H8O2. There we go. Solved. So that's it. So C8H8O2 should be A is the answer. Okay, and if you want more work on these, you can certainly take a look at the notes in class because we've done many of these. All right, so let's take a look at this combustion analysis. So we know it contains carbon, hydrogen, and oxygen. Remember, the carbon comes from CO2, the hydrogen comes from water, and the oxygen is the stuff left over. So if I have 2.48 grams of CO2, I have to extract the carbon from that. So what I'm going to do is I'm going to multiply this by the molar masses of the two things. So 44.11, that's the number. 44.11 grams of CO2 over 12.01 grams of carbon. Right, so grams of carbon is going to go away, and that's going to leave me with grams of CO2 is going to go away and leave me with grams of carbon. I end up with 0.675 grams of carbon. And then we can take that a step further and turn it into moles of carbon. 12.01 grams over 1 mole of carbon gives me a grand total of 0.0562 moles of carbon. So we do the same thing with water. The only difference for the water, so it's 0.510 grams of water. The only difference is the 18 grams of H2O, which is the molar mass of the water. It's 2 grams of hydrogen because I have 2 hydrogens for the whole water. So we have to take into account 2 hydrogens, which weigh 2 grams. Do the math and you end up with 0.0567 grams of hydrogen. And then we can convert 1 mole of hydrogen is equivalent to 1 gram of hydrogen with 1.001, but gives me about 0.0567 moles of hydrogen. Okay, good. And then finally, the last little bit, and this is the hardest part of it, that 1.038 is the entire sample. So the 1.038 grams is going to contain the carbon, the hydrogen, and the oxygen. So if I subtract the mass of my carbon, so 0.675 grams of carbon, or I should say carbon, that eliminates the carbon from the initial mass. Now I eliminate any hydrogen that I have present, 0.0567 grams, excuse me, of hydrogen. That eliminates the hydrogen, and the only thing left is the oxygen. So any remaining mass will be from oxygen. I end up with 0.3063 grams of oxygen is what remains, which is good. Now I want to convert that into moles. So 16 grams of oxygen over 1 mole of oxygen. And I end up with 0.0191 moles of oxygen. Great. And now we're going to do the same thing where I plug it in. Carbon is 0.0562. Hydrogen is 0.0567. And oxygen is 0.0191. Divide by the smallest, which is 0.0191, giving me C3H3O. And there's my answer. C3H3O, which is C. This is, I guarantee you, these are going to come in the form of a short answer, but nonetheless, there we go. Lead carbonate, 1 lead at 207.2, 1 carbon at 12.01, and 3 oxygens at 16 each. When I add all of that up, you should end up with a total of 267.21 grams per mole. There it is, 267.2. So should be your answer there. All right, next up, what is the mass of oxygen in this lead nitrate compound? Again, we're going to do the same exact setup in terms of determining this, determine the part over the whole. So I want, in order to get percent oxygen, I need the mass of oxygen over the mass of my lead nitrate times 100. So what are my values? So I have lead, which is 207.2. 207.2 grams per mole. 2 nitrogens, which is 2 times 14, 28.014 grams per mole. And we have 6 oxygens at 16 each, 96 grams per mole. So the grand total of all of those together for lead nitrate is 331.214 grams per mole. And now I just plug the numbers in. So 96 grams of oxygen over 331.214 grams of lead nitrate times 100 gives me an answer of 29.0%. That's what we should end up with, 29.0% C. Okay. Yeah, so that's pretty much it. These percents are pretty easy. We're going actually kind of the other way around, which should make it much, much simpler. Now let's take a look at, there are X number of moles of carbon atoms in 5 moles. So when we think about this as a whole, this individual molecule here, my C2H6SO has 2 moles of carbon, 6 moles of hydrogen, 1 mole of sulfur, and 1 mole of oxygen. Okay, so 2 moles of carbon atoms, 6 moles of hydrogen atoms, 1 mole of sulfur atoms, 1 mole of oxygen atoms within that one molecule. Okay, so if I have 5 moles of this, I have X5 of these as well. So that means that I now have 10 moles of carbon, 12 moles hydrogen, 5 moles, oh, sorry, not 12, that's not right, 30 moles. 30 moles of hydrogen, 5 moles of sulfur, and 5 moles of oxygen. And of course, we don't care about any of those other than carbon. Carbon has 10 moles, 10 moles, answer is D. Okay. Aqueous solutions. Okay, so when aqueous solutions combine or mix, they're precipitate form. So we have to think about the products of all of these. So the products for all of these are what's going to be important. So again, if I highlight the things, I need to switch the nickel with the nitrate and the silver with the bromine. We're going to end up with NiNO3 2 plus AgBr. Nickel nitrate, what we know about all nitrates, they are aqueous, bromine is solid. So that's pretty much our answer right there. But let's check the rest of them anyway. Now, both of these start with group 1. So I know it doesn't really matter if they switch partners, all those are going to be soluble. So yeah, so no matter which way we look at it, Ki plus NaBr, we simply know that group 1s are soluble. So group 1. Group 1 is always soluble. Much like nitrates, NO3 minus, always soluble. The next one, potassium. So we know that this is aqueous. And when I switch potassium to be with chlorine, we know that that's going to be aqueous as well, just because group 1 is always that way. And then chromium to sulfate. Go. So chromium 2 SO4 3. We know that sulfates are aqueous except for the heavy sulfates. So barium. So yes, just for the heavy sulfates, that's all. And again, we already said KCl is going to be aqueous as well. Heavy sulfates are going to be soluble, but it doesn't matter. Group 1 is also soluble. So next one, these are both group 1s as well. So cesium carbonate plus lithium iodide, group 1, aqueous, aqueous, good to go. Next one, barium hydroxide. This is a heavy hydroxide. All of the heavy hydroxides in group 1 are soluble. Everything else is aqueous, or everything else is solid. So this one is aqueous, heavy group 1s. That's a strong base, heavy group 2s rather. And then potassium nitrate, we know that that's going to be aqueous as well. So we just have to get used to the solubility rules and get used to changing compounds around. All right, next up, the net. So the answer was A. Next up, net ionic equation for the reaction between aqueous sulfuric acid. The aqueous part doesn't matter. Sulfuric acid and sodium hydroxide. So let's take a look at this and let's ignore all of these and just look at right away. I know what the answer is going to be. There's my sulfuric acid, aqueous, plus NaOH, aqueous. Doesn't matter. I know it's acid base, so I already know the answer to this, but let's do it anyway. So because these are aqueous, this is going to be H plus and SO4 2 minus. This is sodium plus OH minus. And now we're going to switch partners. So when I combine together hydrogen with hydroxide and sodium with sulfate, what do I get on the other side? H and OH come together to give me H2O. And that is a liquid. Plus, I'm going to combine together sodium and sulfate, which is aqueous. And because it's aqueous and the complete ionic, I am going to separate it out. So what gets eliminated? Sulfate remains aqueous, sodium remains aqueous. Essentially, it's always the salt that remains aqueous, and that leaves behind just water. So the net ionic is H plus OH minus, both aqueous, yields H2O liquid. Here we go. This is the result of an acid-base reaction at all times. D excuse me. D is the result of that reaction. All right. The following are the following spontaneous or not? Again, spontaneous just means, is it a reaction or not a reaction? So spontaneous means it's going to react when it's combined. Non-spontaneous means it's not going to, so no reaction. So I said no reaction, but not spontaneous is probably a more proper way of saying it. So this is all activity series stuff. Activity has to do with the reactions of these things. So the activity series, we know group 1 is most reactive, group 2 is second, the transition metals are third, hydrogen, and then finally the coinage metals or precious metals. And the precious metals are in a little T at the bottom. So if you look where copper is, copper, silver, gold, copper, sodium, got that backwards, copper, silver, gold, and then on the right you're going to notice mercury, and then on the left you're going to notice platinum. So those right there are the precious metals, okay? And those are the ones that are not reactive, okay? All right, so let's take a look at what we got. So remember, the most reactive will always be the most reactive will be an ion as a product. So if the most reactive is not a product, it is not going to work. All right, so let's see what we got here. I've got nickel and I've got hydrogen. Nickel is a transition metal and hydrogen is just hydrogen. So this one should be, nickel should be more reactive. So more reactive, it should be, if it's more reactive, it should be an ion. Nickel is in fact an ion, therefore this thing is going to be spontaneous, or this reaction will proceed as written. So yeah, so this one will work, but it's going to be spontaneous, so it's not the answer. Next up, I've got copper and I've got hydrogen. By the way, these are all combined with hydrogen, so that's worth a look. So we're combining together with copper. Copper is actually less reactive, so hydrogen is more reactive. Hydrogen is the element, therefore this is the correct answer because this is not spontaneous. Okay, and now let's check the rest of them. Zinc, it's transition metal, it's more reactive. Zinc is in fact the ion, so this is spontaneous. Next one, magnesium, group 2. It should be the ion, it is spontaneous then. And then finally, aluminum, metal, transition metal, not really transition metal, but group 3 metal. It's not group 2, it's somewhere in the other metals. It is the ion, therefore it is spontaneous. And that's all we pretty much do. We want the more reactive metal to be the ion on the other side of the reaction. So the answer to this is B. All right, next up, which of the following are strong electrolytes? So a strong electrolyte, the term we need to know. Strong electrolytes are going to be soluble ionic compounds from the solubility table, as well as strong acids. And the strong acids, you need to know these strong acids: HCl, HBr, HI, HClO3, HClO4, H2SO4, HNO3. So those are the strong acids. Those are the 7 you need to know. All right. In terms of the solubility table, it seems like it's a lot. You should know that always is soluble. Group 1, anything with group 1, anything with ammonia, NH4+, anything with nitrate, anything with CH3CO2 minus or acetate, and they might write it differently. C2H3O2 is another way you're going to see it, but those are always soluble. Soluble with exceptions. Soluble with exceptions are, in fact, I'm just going to actually shift to my complete one here because I have all this here, and I'm just going to annotate it. Here we go. So soluble with exceptions are the chloride, bromide, iodide, except for those 3 ions, which come up again, at least 2 of them come up again in the sulfate. So insoluble, the heavy group 2s plus mercury and lead. So there's a couple of exceptions there, but for the most part, those things are all soluble. Insoluble with exceptions, hydroxides and sulfates. Notice that they have the same exact group 1, and the heavy group 2s count as soluble for sulfates and hydroxides. And then finally, always insoluble, the carbonates and the phosphates. So yeah, again, the only exception being group 1 and NH4+. Group 1 is always soluble regardless of what the anion is. You could just move on from there. All right, next up, what are the spectator ions for KOH and HNO3? So whenever you have a base plus an acid, you're going to get water and the salt. The salt contains the spectators, and here's my work for it. When I break it down to the different ions that we have, the things that go away are the nitrate and the potassium. So those are always the spectators. The salt is always the spectator. Okay, what aqueous solution of, and essentially all this is asking is what is the net ionic equation of this reaction? And there it is. You can pause it if you want to take a look. This is my molecular. This is my complete ionic, and I'm eliminating everything but lead and chloride, the things that actually do something. Okay, well, lead chloride is one of those exceptions. Lead chloride, lead chloride, bromide, iodide, all those are exceptions, but those are the ones you see. Which of the ones is most easily oxidized? Again, activity series tells you if you look at group 1, it easily gets rid of an electron. It really wants to get rid of that electron, and so it's easily oxidized. So group 1 is absolutely easily oxidized. So when you're thinking about what's easily oxidized, just think about the periodic table. Group 1 absolutely wants to get rid of it. All right, 19. 19 is a dilution problem. Anytime we deal with dilution, we have V1C1 equals V2C2. This is the solution that we want to make. So that can be either your V1C1 or your V2C2. In my case, it was 1. And I'm making it from a 6 molar solution. So the question is, what volume do I need from my original concentrated solution to dilute? And so I need 29.3 mils, and then I'll add up to 200 mils to get my new concentration of a solution. Excuse me. All right. Based on this equation, which is the most reactive? So this is just kind of like a chain rule kind of thing here. So lead, nickel react, nickel turns into the ion. Because this reaction goes, I know that nickel is the ion, therefore it is more reactive than lead. So in this case, nickel is more reactive than lead. I have lead and I have silver. Silver, there no reaction occurs. So lead is more reactive because if it were less reactive, they would switch partners or it would become a solid. It's not. So that means that silver is in fact going to be less reactive. So that's what I have here. Lead is more reactive than silver because no reaction occurs. And then finally, same thing here. Copper replaces the nickel. The nickel becomes the ion. The one that becomes the ion is more reactive. Nickel is more reactive than copper. So in terms of chaining these together, I know nickel is greater than lead. I know lead is greater than silver. And I know nickel is greater than copper. We don't really have anything comparing copper to any of the others, but that's what we can say just based on this. So which is the most reactive? Nickel seems to be more reactive than any of them. So B is the answer. All right. Which one has the largest number of moles? So I did a bunch of calculations here. And basically what I did is I started with how the concentration the concentration of my compound. Here it's 1 molar HCl. I multiplied by the volume in liters. So that eliminates liters and giving me just moles of NaCl. But the extra step that I take is what is the number of chloride ions in the compound? So NaCl has 1 chloride. So NaCl has 1 chloride per molecule, but iron chloride has 3 chlorides per 1 molecule. So we do all of those calculations for all of these, and it turns out the second one is the most concentrated. Although it doesn't seem like it because it's half the concentration, there are 3 chlorides for every individual iron molecule, iron chloride molecule. So that's how we end up with the answer B. A solution is prepared by dissolving. Okay, so we're looking for the molarity, and it's always worth looking for what you need. We're looking for molarity. I know molarity is equal to moles of solute, or NH3 in this case, over liters of solution. So we're going to solve this in a different way. I'm going to solve for moles of solute first, and then liters of solution. So here's my calculation for moles of solute, giving me 0.882 moles at H3, and then liters of solution. I'm given grams, but I do have a density. So that's how we go from grams to volume. And I have, so I get a volume from that. Overall, I end up with 3.24 molar solution. And the same thing with every single step. I'm always going to write down what I'm looking for. I'm looking for the molality. Molality is going to be moles over kilograms of solvent. So moles of lithium chloride, I calculate that out based on mass. I know I have 9 grams of lithium chloride if I have a 100-gram solution, right? So if I have 9 grams of lithium chloride, I have 91 grams of water. So 9 grams of lithium chloride at 42.394 grams each gives me 0.212 moles. And then I know I have 91 grams of water, which is 0.091 kilograms, giving me a 2.33 molal solution. The answer is A. And Bela seems to be testing Sadie right now, so I apologize for the barking. All right. And the same thing for the rest of these as well. So what is the percent calcium chloride? Mass of calcium chloride over mass of everything else. So the mass of calcium chloride turns out to be 27.7 grams. And the mass of everything else is mass of the water plus the calcium chloride times 100, 6.88% of the solute dissolved here. Mole fraction. Mole fraction is the same exact thing, only not times 100, and we're looking at moles. So mole fraction is equivalent to moles of what I'm looking for, the solute, over the moles of the whole thing. So if I have 38.5 grams, because I have 38.5% of H3PO4, I convert it into moles. And then I have 61 grams of water, which I convert into moles as well. So moles over moles gives me a mole fraction of 0.103. All right, and I think we have just 2 more. Yeah, 2 more. So how many grams of solution are present? Let's see, we're looking at concentration by. So how many grams of solution are present? So I did kind of talk about this briefly in class. So let me just write out what I have. I have 12.7 grams of solute because I know by mass, that's what I've got. That means that I have 87.3 grams of solvent and 100 grams of solution. So I'm setting up a proportion between these two. for my solution. So I know based on percentage, and I could probably put that, based on percentage, I know that that's the masses that I have. 12.7 to 87.3 is equal to 100 grams of solution. But I have 63 grams of water, which is my solvent. So in order to solve for the grams of solution, I'm just essentially setting up a proportion. 87 grams of my solvent over my 100 grams of solution is equal to 63 grams of solvent over X grams of solution. Solve for it, 72.2 grams. That's a way of looking at it. Again, I didn't really care about the solute there, although I did use it to figure out how much solvent I have present. And then finally, one more mole fraction. Nitric acid, 8.46% means I have 8.46 grams of HNO3 and 91.54 grams of water. Convert them both to moles, and then just plug them into the mole fraction equation, and you end up with your proper mole fraction value. Good. All right. So that's it. Hopefully this helps. If you have any other questions, feel free to let me know.